Welcome back to class again. I was taking few problems. I'll repeat those problems again in the break, which after again this 45 minutes of lecture we'll have it. Let's start off with a new topic, which is about systems. Okay. Systems. So before going to the systems, what we have done is we studied about the signals, we studied the types of signals, we studied the classification of the signals, we studied the operations on the signals, and then we studied some basic signals, which is unit step and delta function, right? Now we are going to study about the systems. Okay. Now the systems, when we going to study, let's define what the system is. Not going into a big definition of the system, I'll just say in simple words, which takes some output, processes it, and which takes some input, processes it, and gives the output back. That is the actual system is. Now when the system is defined, I can define system in continuous time domain, I can define system in discrete time domain. Okay. That is the definition of the system as per the time is concerned. But whether it's a continuous time or discrete time, system has got different types, and few of those types are, first one is linear and non-linear systems. Second one of them is time variant, time invariant, and time variant. Third one is causal and non-causal. Fourth one is stable and unstable. These are the important types. Then afterwards there is a static and dynamic systems, memory and memoryless systems, many other different types of systems also there. Invertible, non-invertible systems, all these systems you will see. Okay. One by one we will take all these systems. So let us first see how to define the linear and non-linear systems, and then sometimes it happens that if you ask about the types of the signals, the student says about the type of the systems. If you ask about the different types of the signals, they say about causal signal, non-causal signal, linear signal, non-linear signal. All these are the system properties, they are not the signal properties. Okay, remember this thing. Linearity, non-linearity is defined only from the system point of view. Time variance and time invariance can be defined only from the system point of view. Similarly, like causality and non-causality, stability and instability. Signal can be bounded or unbounded, but the stability and instability is a system property, not the signal property. The first one, linear and non-linear systems. There are two properties to define the linearity, and those two properties are the principle of superposition and principle of homogeneity. Okay, principle of superposition says if there is a system for which input is xt and gives me output y1t, x1t gives the output y1t, x2t gives the output y2t, Then for the same system, if x1t plus x2t gives the output y1t plus y2t, then the principle of superposition is satisfied. Okay. There is a principle of homogeneity which says that if x1t is the input and if y1t is the output, then k times x1t should give you k times y1t. That is the principle of homogeneity. Any system which satisfies both these principles said to be linear system. That is the simple definition of linearity. Any system which satisfies both these principles, principle of superposition as well as principle of homogeneity, it is said to be a linear system. Okay, now I can write both these conditions simultaneously. I can write ax1t plus bx2t must give you ay1t plus by2t. If this condition is satisfied, system is a linear system. Okay. Now let us take some example. If this condition is not satisfied, of course it becomes a non-linear system. Already we have seen all our electrical network, resistance, capacitance, inductance, they all are linear element. And once they are linear element, we can apply the principle of superposition there in electrical networks, right? Why? Because all the elements are linear. If they would have been a non-linear elements, we cannot apply that. Okay, let's find out. Take some examples. Determine whether the given system's input-output relationship are linear or not linear. Now before we come to this, let me tell you one more thing. There are different ways of representing a system. This way of representing a system is directly by input-output relationship, and that is in time domain. There is another way of representing a system using transfer function. That is possible only for linear time invariant system. There is another way of representing a system by differential equation. That is possible both for linear as well as non-linear system. There is another way of representing a system in terms of the impulse response. We will see impulse response later, how to define the impulse response, and that is defined only for the linear time invariant system. Okay, so presently here in this case I am representing my system using input output relationship. How the input and outputs are related, by that relationship I am representing my system. Okay, now to see whether the given system is linear or non-linear, a simple thing is apply the input x1t and see y1t, apply the input x2t, see y2t, apply both x1t plus x2t simultaneously and see that whether that is equal to y1t plus y2t or not. If it is equal to y1t plus y2t, it is linear. If it is not equal, it is non-linear. So let me write here y1t is equals to x1t plus 3, right? If x1t is the input, y1t is the output. y2t is nothing but x2t plus 3. Right? Now you apply x1t plus x2t simultaneously. x1t plus x2t plus 3. This equals to y dash of t. Now this y dash of t must be equal to y1t plus y2t. See whether it is equal or not. y1t is x1t plus 3, y2t is x2t plus 3. If you add y1t plus y2t, it is not equal to x. This is x1t plus x2t plus 3 is not equal to x1t plus x2t plus 6. Okay. Now here the principle of superposition is not satisfied, and thus this becomes a non-linear system. Okay, in weak sense you can say it is a linear because it represents the equation of line, but in the strict sense it is not a linear system, it is a non-linear system. Try to understand it once again. If you apply the input x1t, you are getting output y1t. If you apply the input x2t, you are getting output y2t. You apply x1t plus x2t simultaneously, you may get some different output, y dash of t. This y dash of t must be equal to y1t plus y2t if you want to specify, if you want to say that a given system is linear. If it is not, it is not linear. Okay. Similarly for this case. This case also, y1t will give you x1 square t, y2t will give you x2 square t, y dash of t will give you x1t plus x2t whole square. Now you know that x1t plus x2t whole square is not equal to x1 square t plus x2 square t. So this is also non-linear. This is also non-linear. Similar is the case with this sine of xt. You give x1t, you will get y1t equals to sine x1t, y2t is equals to sine x2t. Now if x1t and x2t are given simultaneously, this will give y dash t. Y dash t is sine of x1t plus x2t, and of course sine x1t plus x2t is not equal to sine x1t plus x2t, hence this is also non-linear. Okay, sine non-linear, this is also non-linear, this is also non-linear. Let's take the last one. Equals to txt. Txt. See whether the given system is linear or non-linear. Now, derivative, differential operation or derivative operation is a linear operation, so don't worry about that. Xt is independent here, xt is not multiplied with anything. Xt is multiplied with the independent variable. So again that rule is not nullified here. So in this case this represents a linear system because no multiplication of the dependent variable with any other dependent variable or itself. See this example. D square yt by dt square plus y square t equals to txt. Now see, the dependent variable yt is multiplied with itself, and once this dependent variable yt is multiplied with itself, the system becomes a non-linear system. This represents a non-linear system. Of course, this differential equation is a non-linear differential equation. This differential equation is a linear differential equation. Okay. Okay. So try to understand the rule. The rule is very simple. If you find in the equation that the dependent variable is multiplied with another dependent variable or its derivative or itself or with the same dependent variable or its derivative, it becomes a non-linear system. If it is not multiplied, it is multiplied with independent variable or not multiplied with anything, it is a linear system. Next type of system. Similar rules hold good for the discrete time systems also. The next type is second one, time invariant and time variant. Time invariant and time variant. Now, if you have input xt, you are getting output yt. If you shift xt by t naught, you will get output as y of t minus t naught. If this is happening, that means if you are delaying the input by amount t naught, output is also getting delayed by t naught, then time invariant. Else time variant. That means the shifting the input either by delaying it or by advancing it also changes the output to be shifted by same amount of delay or same amount of advance. Okay, that is time invariant and time variant systems. If the shifting is same, input as well as output, time invariant. If the shifting is different, time variant. Let's take an example. Yt equals to txt. See whether it is time variant or time invariant. Let's take y dash t when input is shifted by t minus t naught. Shift yt by t minus t naught, t minus t naught, x of t minus t naught. Now you see whether this and this are same. See this, they both are different. And if they both are different, that makes a system time invariant. Not time invariant, time variant. Again, there is a rule to identify whether the given system is time invariant or time variant or time invariant. But look at this first. I have shifted input by t naught. I got the output y dash of t. If I shift my actual output by t minus t naught, I am getting this. Now this and this are totally different, and once they are different, it becomes a time invariant. Time variant. If they are same, if they would have been same, answer would have been time invariant. But it is not the case here. Let's take another example to see whether it is time variant or time invariant. Yt equals to sine xt. Okay, we have already seen this is a non-linear system. Why? Because I can expand xt. I can write it as xt minus x cube t by 3 factorial plus x5 t by 5 factorial, like this it goes on. Now you see here, in this the dependent variable is multiplied with itself, and that makes the system non-linear. Okay, time variant and time invariant. If I shift input by t naught, I will get y dash t, which is sine x of t minus t naught, right? If I shift yt by t minus t naught, I will get sine x of t minus t naught. Now you see, this and this both are same. That means y of t minus t naught is equals to y dash of t, hence system is time invariant. System is time invariant. Shifting the input, see what is the output. Shift the output, see what is going to happen, and see whether both these are same or not. If they both are same, system is time invariant. If they both are different, system is time variant. They both are different here, they both are same here. Another example. yt equal to x of 2t. See whether it is time variant or time invariant. Now, if I shift xt to x of t minus t naught, I will have y dash t is equals to x of 2t minus t naught. See what I have done here. The scaling operation is done only on the time variable t, not on the constant, right? So once I shift my x of xt to x of t minus t naught, and I put in this, I'll get x of 2t minus t naught. Okay. Now, y of t minus t naught is equals to x of 2. Now t minus t is shifted by t naught. T minus t naught. That becomes x of 2t minus 2t naught. Now see this. Y of t minus t naught is this. Y dash of t is this. By shifting the input, I am getting this. By shifting the output, I am getting this. Now both these two are different. This is 2t minus t naught and this is 2t minus 2t naught. Hence the system is time variant. What about the linearity of this? Whether the given system is linear or non-linear? Yes, apply the property of the linearity. If x1t is the input, I will get y1t, x1 2t, y2t, x2 of 2t, x1 of 2t plus x2 of 2t going to give you y1 of t plus y dash of t. Now this y dash of t is equals to y1 of t plus y2 of t. Hence system is a linear system. It is a linear time variant system. Okay, so this is how we find the linearity, and this is how we find the time variance or time invariance. Text. How to identify? Okay, this is the way to identify, but how? By just looking at the expression of the input and output to identify whether the given system is time variant or time invariant. See this. If output and input are related by some function of time, if input and output are related by some function of time, it is going to become time variant system. This is always time variant. If input and output are related by some function of time, it is going to become time variant system. Okay? If it is not, definitely it is going to be time invariant. Okay. The next type of system, causal and non-causal system. Causality and non-causality. See now, the causality meaning is the non-anticipative nature. Without the cause, there cannot be any effect, and that is the meaning of causality. If system is showing some effect, if system is giving the output before even the input is applied, that means such systems are not practical, and those systems are known as non-causal, because without the cause, the effect is going to come, and that is known as non-causal system. If with the cause some effect is coming, that is a causal system, and that is the meaning of the causality and non-causality. See, if yt equal to x of t minus t naught. Okay, if I want to know what is the value at y equal to 0, y equal to 0 is nothing but x of minus 2. That means if I am looking at time t equal to 0, I am dependent on the past value of the input. Yes, the past value of the input, it is there, it can be stored in the memory. In this case, the system becomes a causal system. Take this example, yt equal to x of t plus 2. In this case, y0 is equal to x of 2. Now see this. X of 2 is a future value. This value is not yet come. And I am getting the output at y of 0, which is dependent on x of 2. How this is possible? Of course, practically it is not possible, but such type of systems are known as non-causal systems. If the output of the system depends on the future value of the input, that becomes a non-causal system. If the output of the system depends either on the present value or on the past value of the system, or both, then it becomes a causal system. That is the definition of causality. Okay, that you can see this. What about this? Yt equal to x of minus t. What about the causality, whether the given system is causal or non-causal? See, if you look at y of 0, it depends on the present value. Minus 0 is nothing but x of 0. Yes, no issue. But if I look at y of 1, let's say I am looking at y of 1, it depends on x of minus 1. Yes, it is true. That means when my values of t is greater than 0, it always depends on the past values of the input, and that represents a causal system. But if I look at this, y of minus 1 corresponding to x of minus 1, that becomes x of plus 1. Now y of minus 1 is the present value where I am looking. It depends on the future value of the input, and once it depends on the future value of the input, that becomes a non-causal system. So finally this system is a non-causal. Either it should be causal or it should be non-causal. It doesn't mean that for some values of time it represents a causal behavior and for other values of time it represents a non-causal behavior. It should be causal or non-causal for all values of time. Okay? If it is specified in the question that what will happen for the positive values of t, what will happen for the negative values of t, that is a different case. Okay? Then accordingly you have to check. I can say that for positive values of t, it is causal. For negative values of t, it is non-causal. But overall, as a system, it is a non-causal system, because system does not depend on system should not depend on time. That as the time is changing, system behavior is changing. Actually, okay. But mathematically, yes, it is possible. Similarly, yt equal to x of 2t. It's causal or non-causal? It's very simple. If I look at y of 0, I will get x of 0, no issue. It is present value at t equal to 0 depends on the x0 only, present value of input. But what is y of 1? Y of 1 is nothing but x of 2. That means when I am looking at time t equal to 1, I am getting the input. I depends on the future value of the input, and that is not practically it is not possible. That means I am getting the output by predicting the future value. It is not possible. So that it represents a non-causal system. Now again here, if I put the negative values of t, if I put y of minus 1, I will get x of minus 2. X of minus output you are getting at t dot k. Now see what is happening. When the t value is 0, output is 0. As the t value is increasing, output is increasing. Finally, when t is tending to infinity, what happens to the output? Output will also go to infinite. That means as the time is increasing, output is increasing, system is an unstable system, because it should not happen. Finally, system should converge, it should not diverge. Okay. Okay, let's take a break for 5 minutes and then we'll start off. We'll do some problems on the stability and instability of the system. Let us take a few problems which have been asked by the students from different places. Rohit from Mumbai is asking, sir, what is u of 0.5 in discrete? Rohit, see, if I plot this u of n in discrete domain, the value of n is always an integer value, right? Once it is an integer value, n equal to 0.5 does not exist, right? And if it does not exist, there is no such value exists for this, and you can say that it is 0 or does not exist, right? Remember, in discrete time domain, the value of n is always an integer value, either positive or negative or 0, right? No other values of n are acceptable, so in this case also it becomes 0. Unmesh from Pune, 2005, ut and u of minus t equal to 0, it took, whereas it is 2. No, Unmesh, you are again doing the mistake. See, I give the 3 definition of ut. One definition is this: t greater than 0, 0 for t less than 0, ut equals to 1 for t less than 0, 1 by 2, t equal to 0, 0 for t less than 0. Another definition of ut is this: 1 for t now you see, you will get different answer if you take different options here. If you take option as this, if you take ut as this, then what you are doing is exactly right, because at t equal to 0 it will give you answer as 2, right? But if you take this as a definition of ut, you will get the right answer. In most of the books in signal systems, this definition of ut is considered for finding the even part and odd part of ut. That's why I told in the beginning, let's consider this definition of ut. Okay? Otherwise, whatever you are getting, that is also right, because you are considering this definition of ut. How to find the period of a complex number? Actually, Siri from Nellore, complex number is a one number. You cannot find the period of that. Okay, if it is a complex signal, you just find, suppose if it is cos omega naught t plus j sin, let me write, cos 2 pi by 5t plus j sin 2 pi by 5t. Right? Find the period of 2 pi by 5, sin 2 pi by 5. You will get the period of this. Complex number doesn't have any period because they are only just one number. Monica from Delhi, sir, please draw or explain how to draw x of 3t plus 2, x of 0.5t plus 2 for any xt. Until and unless xt is not known, how can I draw that? Once you give me some x of t, see, if you want to plot x of 3t plus 2, and if xt is given to you, first thing is you shift it by 2 is a time advance or left shift, and then you scale this by 3 you will get 3t plus 2. This leads to compression. This is all what I can. So once I know xt, I can do it. If xt is not known, I cannot do it. Similar things, Pallavi is asking the same thing. Until unless xt is not known, I cannot plot it. Okay, you tell me what is x of t, I can draw it. Sri from Hyderabad is asking, sir, what I mean to ask at n equal to 0, whatever does not represent delta n. See, yes, again we are coming to the same thing. At n equal to 0 it is 2, and for remaining values of n it is 1. So what is, it is just like this. There are two signals. One is this. This all values are 1, and one signal is this, which is delta of n. Okay. Now this signal and this signal, if I add, what I will get at n equal to 0, this is also 1, this is also 1, that becomes 2. And for remaining values of n, this is 0 and this is 1, so that's why it is 1. So that's why at n equal to 0, I have written u of n plus u of minus n is nothing but 1 plus delta of n. That's why I written delta of n. I am not saying that n equal to 0 it is delta n, but n equal to 0 it is 2. And you see here, when you put n equal to 0, what you will get? 2 here. But when you put any other value of n, what you will get? Only 1. Okay, that's why it is 1 there and 2 at n equal to 0. How 8 cos 2t dot xt is linear? See, now again the rule is same. The dependent variable is not multiplied with itself or with its derivative or with its another dependent variable. Now look at this. Yt equals to, this is Rajiv from Delhi, yt equals to 8 cos 2t dot xt, right? Now this xt is different, cos 2t is different. What you can do is, you will get yt is equal to 8 cos 2t x1t. You will get y2t, which is equals to 8 cos 2t x2t. You give x1t plus x2t simultaneously, you will get y dash of t, which is equals to 8 cos 2t x1t plus x2 of t. Now you expand this, you will get 8 cos 2t x1t plus 8 cos 2t x2t. Now this is nothing but y1t, this is nothing but y2t. Now see, y1t plus y2t is equal to y dash of t, and the system is a linear system. Okay, x square of t is causal or non okay, this is Rajiv from Delhi, whose answer is yes, it is a linear system. Okay, Rajiv. This is Neha from Delhi is asking, is real part of xt is linear or non-linear? It is a linear system, because if you give yt equals, y1t is equals to real part of x1t, y2t is equals to real part of x2t, you combine both the things, you will get y dash of t is equals to real part of x1t plus x2t. They can be taken inside, real part of x1t plus real part of x2t, which is nothing but equals to y1t plus y2 of t. Hence it is a linear system. X square root of t, yes, it is not a causal system. Yt equals to x under root of t. Okay, now you see, you just find what is y of 4. Y of 4 is nothing but x of root 4. So you got x of 2. No problem, this is fine. You put y of let's say 0.81. Y of 0.81 is x of under root of 0.81. What is this? X of 0.9. Now you see, y of 0.81 you are looking, and you are dependent on the future value of the input. That makes the system non-causal. Okay. Sir, what is the period of delta sin t plus delta cos t? What is this delta sin t plus del cos t. If this is representing a derivative of sin t and cos t, then the answer is just find the period of sin t and find the period of cos t and take the LCM, you will get the answer. What does y dash t in linear time invariant and variant topics means? Y dash t. Y dash t is nothing but the derivative of yt. It is simple. Y dash t is a representation of representing a derivative of yt. Instead of writing dyt by dt like this, you are writing as y dash of t. That is the simple. If it is d square yt by dt square, you are writing as y double dash of t. Okay, that is the thing. Rajiv from Delhi is asking e to the power minus 2 plus jt. Yes, Rajiv, let's see this. Rajiv from Delhi. Rajiv, your question is xt e to the power minus 2 plus jt is periodic or non-periodic? See Rajiv, it is very simple. E to the power minus 2t, e to the power jt, right? Now e to the power minus 2t has got this nature, right? E to the power jt has got cos t plus j sin t. And if I take only cos t or sin t, yes, if I take only this alone function, it is periodic. But this alone function is multiplied with e to the power minus 2t. That makes the actual signal going tapering like this. Now you see, the signal is changing with time, the amplitude is changing with time. Now it is, you cannot say that this will repeat after a certain value. That makes the given signal as non-periodic signal. Okay, so the best way is if you encounter some signal, you just try to plot it and see whether it is repeating or not. If it is repeating, fine, but if it is not repeating, it is non-periodic signal. Now we see here, the amplitude here is different and this amplitude will never come. It will never come here. This amplitude is different and this amplitude will never come. Okay, that makes the given signal as a non-periodic signal. Till how many values we have to substitute and check whether it is causal or non-causal system? Generally, it's very subjective. See, sometimes it happens you can just check 2-3 values, you will get the answer, and sometimes it happens you may have to boggle your mind more and more to get the answer. Okay, it's all comes with practice. More and more practice will let you know how to go about to check this non-causal and causal systems. Rohit, non-causal and anti-causals, I'll tell you the difference once I'll do the Laplace transform, because in Laplace transform these two things comes when we study the region of convergence, what is non-causal and what is the anti-causal thing. But let me tell you, both non-causal and anti-causals are more or less same only. It's only a different wording, different nomenclature is given to them, but they all represent a non-causal thing. Sir, Vikas from Bangalore. Sir, can we generalize it by saying if the input is scaled by a factor, then it is a not causal and time variant? Please tell me whether there is a difference between anti-causal and non. Yes, you can generalize it. If the input is scaled by some factor, that is a non-causal system and it is time variant also. There is a difference. Once we study the region of convergence, I'll tell you what is the difference between anti-causal and non-causal system. There is a difference, but this is not the time to tell the difference because it will be more clear once we study the Laplace transform. Rohit from Mumbai. It is true that parabolic and ramp signals are always unstable. Parabolic and ramp signals are always unstable. Yes, they are always ramp signals are. No, it's not about the signals, Rohit. The parabolic and ramp, they are unbounded signals. I should say this. Okay, they are not unstable. They are unbounded signals, and they are always unbounded. Okay, because with increasing value of t, what is happening? Their value is also increasing. So that makes the system unbound, and that's why this signals becomes unbounded signals. Okay, stability and instability are the words to be used with systems. Janani R from Chennai, what is meant by bounded input and bounded output? See Janani, it is very easy to understand, not much difficult. If your input xt is lying between infinity and 0, it is bounded input. If your input yt is lying between infinity and 0, it is bounded output. It means that xt is also you can quantify it, you can give some number to it, and for yt also you can give some number to it. If this condition is there, they are bounded. If it is becoming infinite, they are unbounded. It's very simple. Please comment on linearity and stability of delta signal and step signal. See again and again I am repeating the same thing. Signal cannot have the linearity property and stability property. Okay, it is a system only which can have the linearity property and stability property. Try to understand this thing, because delta signal and step signal, if they are the impulse response of a system, linear time invariant system, they will be both stable as well as linear. Okay, but they are, if you treat them as a signal, then you cannot comment anything on the linearity and the stability of them. Okay, so first, once we will come to the linear time invariant system, there we will study the delta signal and step signal, and then we can comment something on that. So whenever signal is there, it cannot be linear, it cannot be stable, it can be only bounded, okay, not stable. So both from Chandigarh. Sir, is this correct statement? The same system may be causal or non-causal, depends on the value of the variable or dependent function of the system, whether it's positive or negative. Just let me try to understand it. The same system may be causal or non-causal, depends on the value of the variable of the dependent function of the system, whether it's positive or negative. Yes, that statement is true. The value of the variable is dependent function. We have seen this. You take this, yt equal to x of minus t. Now you see, yt equal to x of minus t. If I put the positive values of t, it is causal. But if I put the negative values of t, it is non-causal. Okay. So if the positive values of t are there, it becomes a causal system. If negative values of t are there, it becomes a non-causal system. Acha. Monica, is very simple. If you want to draw x of minus 3t plus 2, you have x of t, shift it and make it x of t plus 2, right? And after x of t plus 2, you scale it by 3, becomes x of 3t plus 2, shift left by 2, that is known as time advance, scale by 3, that leads to compression, and after compression you do time reversal. That will give you x of minus 3t plus 2. Okay, that gives the whole process of, if you know x, if you give me x of t, I can do all these things. But whatever x of t you have, you do this process, you will get the right answer. Pallavi is asking e to the power minus x square. I think it is e to the power minus x square. It is bounded or unbounded? Yes, it is bounded. You plot this function, very easy. For different values of x, e to the power minus x square is something like this. Now you can see, for any value of x, it is not infinite, right? It is always bounded. So the answer is yes, it is bounded. Yt equal to x of t square, is it linear? Yes, it is linear, because you see the xt is it is not multiplied with anything. The independent variable is multiplied, but the dependent variable is not multiplied with anything, and that makes the system as causal. No, sorry, that makes the system as a linear system. Veena, we have taken this example, yt equal to x of sin t. Yes, it is a non-causal system. It is not causal. Yt equals to x of sin t. If I put y of minus pi, it depends on x of 0, and that makes the system as non-causal system. Okay. So we are done with the questions which we have from different people. Okay, now we were doing about the stability and instability. Let's come to the topic where we left. Stability and instability. how to determine for a given system whether it's stable or unstable. Now to determine whether the given system is stable or unstable, we have to give a bounded input to the system, and then we have to see whether the output is bounded or not. If output is also bounded, system is a stable system. Bounded input means xt should be within finite value, and if yt is also finite for all values of t, system is bounded system. For example, yt equals to e to the power xt. Now see this. Even if you give a bounded input to x of t, like if x of t is equals to k, where k is some finite value, yt is nothing but e to the power k, and e to the power k is a finite value. Even if k equal to 100, e to the power 100 is some finite value. That means if the input is bounded by fixed value, output is also a fixed, output is also becoming constant. So in that case, system is a stable system. Okay. We'll take one more example. Yt equals to 8 cos 2t dot xt. Now see this. If xt is bounded, means I can put xt some finite value k. Okay, bounded value k, where k is some constant. Yt is nothing but 8k cos 2t. Now see, whatever be the value of t, the maximum value and the minimum value of cos t is plus minus 1. When it multiplied with 8k, that also become plus minus 8k. That means if xt equal to k, plus minus 8k is also bounded, and if that is bounded, yt is bounded, and if yt is bounded, system is a stable system. Thus this represents a stable system. Okay. That is way to check whether the given system is stable or not. You give some input which is bounded and check whether the output is, how the output is behaving. If the output is also bounded, system is said to be a stable system. Okay. So these are few important types of the system which we have to see. Then there are static system and dynamic system. Static systems are those which depends on the present value of the input. Dynamic systems are those which depends on the present as well as past or as well as future value of the input. Right? Then there are memoryless and memory systems. Memoryless systems are those which does not depends on the past value of the input, and memory systems are those which depends on the future value of the input. Okay. Then there are invertible systems. Invertible and non-invertible system. Invertible system, for example, if there is a system whose input is x of t, I'll get output y of t. We are seeing invertible and non-invertible system. If this system is invertible, then I will have another system to which if the input is y of t, I'll get output x of t. Now system S2 and S1 are invertible of each other. If the input is x of t, output is y of t, and if input is y of t, I should get x of t. If this is happening, then S1 and S2 are invertible of each other. If it is not happening, then it is not invertible of each other. For example, let's take yt equals to x square of t. Okay. Now this is not an invertible system. Why? Because if I put xt equal to plus 5 or minus 5, I am going to get yt equals to 25. Right? Now if this 25 is input to another system, Both values are giving me 25. Now if this 25 is input to another system, let's take that maybe xt equals to root of yt. Then if 25 is input to this, whether this 25 has come from plus 5 or whether this 25 has come from minus 5 cannot be determined, right? That means in this case the system cannot be an invertible system. Now how to identify whether the given system is invertible or not? The rule is very simple. What we have to do is we just have to see whether there is a one-to-one mapping is there from the input to output or not. If one-to-one mapping exists, system is an invertible system. If one-to-one mapping does not exist, system is a non-invertible system. One-to-one mapping means for each unique input there is a unique output. If there is x1, x2, x3, y1, y2, y3, for each unique input you have unique output, system can be invertible system, otherwise it cannot be an invertible system. That is the simple rule for finding whether the given system is invertible or not. We will see more about invertibility once we will do the impulse response, Laplace transform and other things. Okay. Now we have to particularly look about the linear. Now we have to particularly look about linear time invariant systems and what happens when the input is passed to a linear time invariant system. Okay. So why we are looking especially for linear time invariant system is because from now onwards whatever we study, whatever the system analysis we do only for linear time invariant system. If the system is not linear, if the system is not time invariant and both, then we cannot have the transfer function of the system. Transfer function of the system is nothing but we will see in the Laplace transform how to find the transfer function of the system. Okay, that is something which is transformed to another domain, and there we analyze some different properties of the system like poles and zeros of the system to determine whether the given system is stable, to determine whether the given system is causal or not. Now see, if the system is not causal and system is not stable, it cannot be practically realizable or physically realizable, because there is no system which can predict the looking at the causality point of view, there is no system which can predict the output without giving the input, right? So it has to be causal. Until unless input is not given, output should not come, right? So it has to be causal. Second, it has to be stable also. Why? Because if it is not stable, then system is of no use. It will work for some duration of time, after that it will go bad or it will get damaged. So both the things should be satisfied and both the things are compulsory. Apart from linear or time invariant, system should be both causal as well as stable. So we have to analyze the system and we have to find out under what condition system is going to become stable, system is going to become causal. All these things we will study when we study the Laplace transform, Z transform and other frequency domain representation. Now coming to the linear time invariant system, we will study another important topic, and that is known as the impulse response. Impulse response of a linear time invariant system. What is the impulse response actually means? Okay, let me write the heading as linear time invariant system. Linear time invariant system. Up till now we have represented a system by yt is equals to input output relationship xt comma t. Now we will define the system using an impulse response. Now what is this impulse response? Let us try to see that. And there is one more phenomena in this which is known as the convolution, that also we will see now. Impulse response. A system is given to you, a black box, and you want to identify what is there inside the black box. Okay, so what is one way? Either you open it and see what is there inside the black box. For seeing what is inside the black box, it's nothing but you want to see the behavior of the system, right? Other way is you try to give some input and see how it is behaving. So particularly there is possibility that different input may give different behavior. But actually whatever you want you may not get. Actual behavior of the system or the characteristics of the systems are not known to you. And you cannot determine it by giving any type of different input. So now what we will do is, At the input of the system, I'll give a special input, and that input is an impulse. Okay, and I'll try to see what happens at the output. Whatever is there inside the system, that will come at the output. And once whatever is there inside the system as a response, if it comes outside, my job is done. And that's what I want to determine. So, for linear time invariant system, I'll first write what is convolution. And from convolution, I'll explain what is an impulse response. So, convolution expression is yt is equals to minus infinity to infinity x of tau h of t minus tau d tau. Okay, just assume that xt is one function, ht is another function, and there is a convolution taking place between this. Similarly, there is y of n, which is summation k equal to minus infinity to infinity x of k h of n minus k. Convolution operation is commutative, and I can write this also as minus infinity to infinity h of tau x of t minus tau d tau. I can write this as k equal to minus infinity to infinity h of k x of n minus k. Okay, this is a formal definition, and the formal, what you can say, the actual formula for convolution. This is the way the convolution is done. There is some variable x1t, some variable x2t, they are shifted, multiplied, many things are done, and then finally it is calculated. Okay, this is okay, fine. Let's see actually what is happening once I am doing the convolution. Now this convolution is possible only for linear time invariant system. For other type of system, if it is not linear or if it is not time invariant or any one of these, this is not possible. Okay. Now see, what does this convolution mean? If I want to convolve two things, if I want to convolve, let's say there is one signal, one pulse, magnitude A1, B1, A1, pulse width is B1 minus A1. There is another pulse A2, B2, capital A2. Okay, I want to do the convolution of both the things. It is denoted by a star operator. B2 is greater than B2 minus A2. Condition is B2 minus A2 is greater than B1 minus A1. A1, A2 can be anything, there is no condition on that. That means this pulse width is more than this pulse width. Okay. Tell me, if input, this input is there, and this is the system response. If I want to send this input into this system, what should go first? This part or this part? First t equal to 0 will go, and then finally t equal to 1, and then finally t equal to 2, right? That means the one operation which I have to do here is I have to reverse this, and then I have to insert into the system. That is required. What I have to do is I have to first reverse it, and then after reversing it I have to insert it into the system, so that one by one all the inputs can go into the system, they can be processed, and finally the output can be given outside. Okay, this is the thing which I want to do. So the first operation which involves in convolution is the time reversal operation. So I'll do the time reversal of this, and then time shifting. So let this be equal to x1 of t, this be equal to x2 of t. This is t, this is also t. Now change the variable. You change the variable because if you look in the formula of convolution, yt is minus infinity to infinity x of tau h of t minus tau. Okay, so you change the variable, we can write it as minus infinity to infinity x2 of tau x1 of t minus tau d tau. Right? So instead of t, I'll make it here tau. Instead of t, I'll make it here tau. Now from x1 of tau, I need x1 of t minus tau. What should I do? x1 of t minus tau, again apply the time shifting property and time reversal property. You will get it as this. T minus a1, and this is amplitude is a1. This one is your x1 of t minus tau, and this one is your x2 of t, x2 of tau. Okay. Now we got x2 of tau, which is this. We got x1 of t minus tau, which is this. Okay. Now what I am doing? Now see at this. If I change the value of t, what will happen? Suppose if I put the value of t equal to 0, then this will become minus b1 to minus a1. If I increase the value of t, then what will happen? This particular thing will get slide into this. Okay. As I increasing the value of t, this whole thing will keep moving inside this, keep moving away like this. So from the system point of view, once I increase the value of t, this will keep on inserting into the system. Finally, it will go completely inside the system, and if I continuously increasing value of t, it will come out of the system. Okay. Finally, after that, there is nothing inside the system. System will not get anything. So only when it starts moving into the system, system output starts coming. Okay. Once it is totally inside system, system output is there. Once it is coming out of the system, system output is there. Once it comes totally out of the system, system output is 0. Okay. So system output starts once it's totally going in. Once it is touch the system input system, and then it is going inside, and then finally it comes out. Till that point, system output will be there. After that, system output will not be there. So let's try to do how to do this convolution, and then after this convolution, we will see the impulse response. Okay, that will help to know this how this impulse response is. Why this impulse response is so important. This is nothing but a signal passing through a linear time invariant system, how it behaves. Okay, to see, first thing. Suppose if t minus a1 is lesser than a2, then there is no common region here. If t minus a1 is lesser than a2, t minus a1 lesser than a2, no common region, yt equal to 0. Okay, this implies t lesser than a1 plus a2, yt is 0. Yes, that is true. If the value of t is lesser than a1 plus a2, there is system, the input is not yet reached the system, it is away from the system, so system will not give any output. Second, if t minus a1 is greater than a2, yes, now in that case, input, this particular thing has gone into the system. T minus a1 greater than a2. And it is getting into the system, slowly it is getting into the system. Remember this condition, b2 minus a2 is greater than b1 minus a1. Time will come, this whole pulse will get into this, because this pulse width b1 minus a1 is lesser than b2 minus a2. T minus a1 greater than a2 and t minus b1 is lesser than a2. Up till this point. Now up till this point, what will happen? I can write my yt as, the figure of this will look something like this. So I can write this integral as a2 t minus a1 a2 t tau, because the value of this is a1, value of this is a2, so this becomes t minus a1 plus a2 a1 a2. This is yt for second case. This will for this range of t greater than a1 plus a2 lesser than a2 plus v1. So during this case, what will happen? As this thing is getting into this, the common region is keep on increasing. That's why you have positive slope. The output will also be keep on increasing. Okay, and finally, once it goes totally inside the system, the output will become constant, and then it will remain constant up till the point this thing completely traverses into the system. And finally, when it starts coming out, output will also start decreasing slowly. This is the second case. Let's take up the third case. Third case. Third case is this. This is your bigger pulse and this is your smaller pulse. It has gone totally inside this. This is t minus b1 and this is t minus a1. This is a2 and this is b2. This is a1, this is b2. Now this is the case. In this case, t minus b1 is greater than a2, t minus a1 is lesser than b2. Now in this case, this area is constant. Even if I take this pulse and if I keep on rotating within this area will remain same, it will not change, right? So I can write yt as integral t minus b1 t minus a1 a1 a2 d tau. This is equal to a1 a2 b1 minus a1. Constant, does not depend on t. Here it depends on t with positive slope, that means it is increasing. Here it is constant, that means up to this range of t, the range of t is a1 plus b2. This is the case third. This was the second case, and that is the first case. Okay, third case is over when the signal is something like this. Now comes the fourth case where the signal is going out of the system. I'll draw it here. In this case, t minus a1 b2 t minus b1 a2 a1 a2. This is the common region. Now once it is coming out, this common region will keep on decreasing. Then we will see that there will be negative slope in our output. Now output yt is nothing but t minus b1 to b2 a1 a2 a2 okay a1 a2 d tau. This is equals to a1 a2 b1 plus b2 minus t. Okay, so you can see here this is a negative slope and here it was a positive slope. Positive slope, why? Because signal is getting inside into the system, the common region is increasing, the output is increasing. Negative slope, signal is going out of the system, the common region is decreasing, output is also decreasing. This happens for the values of t greater than a1 plus b2, t lesser than b1 plus b2. Okay. This 4 different cases are there. After that, when the signal is totally out, output is 0. Okay. Now let us draw the complete picture, complete figure what happens at the output yt, how to plot the output yt. For that, I'll rub this part and consider the 3 regions. The first region is this. Output starts coming from A1 plus A2. It goes up to A2 plus B1. Then here A2 plus B1 to A1 plus B2. Then finally B1 plus B2. Output increases continuously up to this point. Then it remains constant up to this point, then it decreases finally up to this point. The value of this is A1 A2 B1 minus B1. A1 A2 B1 minus A1. Okay. So it looks like a trapezium, and definitely always it will be like this. When there are 2 unequal pulses of different shapes, 2 pulses of different pulse widths, you will get something like trapezium. Okay. This convolution I have taken only because this particular pulse convolution will be required when we will study the communication match filters. At that time also we required similar kind of approach of finding the output of the convolution when 2 pulses are there. Okay. So you can see it once again. We have taken the few cases when time is lesser than A1 plus A2, output is 0. When time is lying between A1 plus A2 and A2 plus B1, the output is increasing. Output is constant between this region. Output is decreasing between this region. Okay. Few particular things which we can observe here is the range of convolution, from where to where the convolution exists. You see, our 2 pulses are there existing from A1 to B1, another pulse existing from A2 to B2. The range of convolution is nothing but the sum of the lower limits and sum of the upper limits. Sum of the lower limits A1 plus A2, sum of the upper limits B1 plus B2. That's the range of the complete convolution. Okay. Beyond this, convolution will not exist. So that is one important thing which we can note here. I can write here the range of convolution sum of lower limits So once you do this by shifting property, I am getting this. Similarly, apply the shifting property here. What is T0 here? T0 is 0. Substitute that by here at 0, that becomes, because what is with what range with what variable I am integrating it? I am integrating with respect to tau. Here I am integrating with respect to t. So they are both one and the same thing. But this ht is independent variable, so this will remain h of t. So yt becomes h of t. Now see, when the input is impulse response, whatever I am getting at the output, that is nothing but the system characteristics. That is ht. That's why this is known as the impulse response. Only when the input is an impulse, I am going to get what is there inside the system at the output, and that's what I want to know. I want to know what is there inside the system. Inside the system is nothing but h of t. How will I know what is that h of t? At the input you give x of t. You input you give delta of t. Once the delta t is there, whatever is there, system will throw it out. And that is nothing but impulse response. You can apply to this also. You can say, okay, yt is equals to minus infinity to infinity h of tau delta of t minus tau t tau. Now you see, what is t naught here? T naught is nothing but t, so that becomes h of t. Okay, that's how the impulse response plays an important role, especially for linear time invariant system. If the system is not linear and time invariant, this itself is not valid. This itself is not valid. The convolution formula and convolution relationship is valid only for LTI systems. Let's do some more convolution. What is the value of this? Not in this way. See this. What is the output of these systems? They all are linear time invariant system. If xt is the input, delta t is the response, what is going to be the output? Y of t. If x of t minus 2 is the input, delta t is the system response, then what is the output? See, it's all very easy. Just have to follow the relationship of convolution. Yt is this, minus infinity to infinity. You can write here x of tau delta of t minus tau d tau. So this becomes x of t, because t naught here becomes tau. So to substitute t naught becomes here equal to t. Substitute t naught equal to t here, you will get x of t. Second case, yt is equals to minus infinity to infinity x of tau minus 2 delta of t minus tau t tau. So here t naught is again t. Substitute here, you will get x of t minus 2. In this case, let us take a generalized case. delta of t minus t naught, delta of t minus tau t1, minus infinity to infinity x of tau minus t naught, delta of t minus t1 t tau. Now what is t naught here? T naught is t plus tau, sorry, t minus tau 1. So that becomes x of t minus tau naught minus t1. So now if you substitute the different values of t naught and t1, you will get different answers there. Okay, let us take break for 5 minutes and we'll analyze. We'll Coming to the questions which has been asked by you, this is Monica from Delhi. She has, yes Monica, what you said is the first is right, because if you do scaling first and if you do the time shifting by +2, then you are going to get a wrong result. But the correct way is x of 3 t plus 2 by 3, what you have done, and that is the right way of doing this. See what, if I want x of 3t plus 2, then if I do scaling first, I will get x of 3t, and if I do shifting first, I should do 3t plus 2 by 3, which is x of 3t plus 2. That is the right way. But instead of shifting it by 2 by 3, if you shift it by 2, then it's going to give a wrong result, which is nothing but x of 3t plus 6. Okay, so the right way is this. Now coming to the my thing, what I did, there is a relationship yt equals to x of 2t, right? The input is xt, so for which yt is nothing but x of 2t. Now if I shift my input by t minus t naught, my output y dash t is nothing but x of, again see, the scaling operation is done only on the variable t, not on t naught, so that becomes 2t minus t naught. That's what I did, and that's what I told. So it is not contradictory. I told that scaling operation or shifting operation should be done only on the variable t, not on the constants. Okay, here you are doing the scaling first and then you are shifting the time variable t, right? So once you are doing the time variable t, it is getting like this. Otherwise it would have been different result. Now this becomes, yes, this is what I said. Rohit is asking from Mumbai. Suppose xt is stable and bounded. So if we integrate or take derivative or take modulus of xt, what will be the status of stability of the xt? If you find the derivative of xt or take the modulus of xt, or if we integrate it, what is the stability of xt? Xt is what? Xt is system. Okay, I think you are assuming that xt is an impulse response of the system, and if you find the derivative, modulus, and if it is stable, even if you take the modulus of that, it's going to be stable only. If you take the derivative of that, it's going to be stable only. Even if you take the modulus of that, it's going to be stable. Integral and derivative operations not going to change. If the impulse response of the system is x of t, as what you are saying, the integral and derivative is not going to make the system as unstable. It will remain stable only. If bounded system has a point of discontinuity in it, so will it be stable? If a bounded system has a point of discontinuity in it, so will it? The discontinuity doesn't mean, see, if a bounded system even has a point of discontinuity, only thing is that, I'll tell you in the next class, even if the system responses have got some discontinuity, but the total net area under the system response, if it is finite, system is going to be in a stable system. Okay? Even if it has got discontinuity, yes, if the discontinuity is of infinite height, if the infinite size, then it could be an unstable system. But if the discontinuity is of finite size, it will be a stable system. Is integral, Vikas from Bangalore is asking, is integral and differential operators are causal and linear? See Vikas, we cannot determine the causality from integration and differentiation. What we can determine is the linearity. Both integral operation and the differentiation operations are the linear operations. Okay? Until and unless the range of the integration and is not defined, we cannot say anything about the causality. But yes, we can always say the integration and differentiation operations are the linear operations. So if the integral and differentiation are the part of the system, that becomes a linear system. Only thing is that we know that differential, there are two types of differentiation equations, but alone a derivative is a linear operation. Rohit from Mumbai is asking, sir, what is the difference between autocorrelation and convolution? Rohit, at this point of time, I can say only one thing. The convolution is nothing but an output of an LTI system when some input is given, right? That is convolution. How to determine the output of the system when the input is given to the system. Autocorrelation is a similarity between the two different signals, or not two different signals, on the same signal. How much they are autocorrelation from sample to sample. Okay, but formula wise, if you look, they have got similar properties. At some point, the output of the convolution and the autocorrelation can be same. I'll tell you when they are going to be same, not today, but at later stage, because if there is a symmetry in the input, or if there is symmetry in the system response, then both autocorrelation and convolutions, if you do apply the formula of autocorrelation convolution, they will appear to be same. Okay. So both from Chandigarh is asking how impulse response gives complete behavior of the system. Please explain with practical example. See Subodh, let me give you a real practical example only. What happens is, in a normal condition, let's take an example from the life itself. In a normal condition, everyone behaves normally. How the things, if you want to know the real nature of anyone, then what you should do, you should put him under certain abnormal conditions, the conditions or such circumstances which are not favorable to him. In that circumstances, how the person will behave will show its real nature, right? If a person is behaving correctly, means as per your expectation, that means you know his nature, whatever you have predicted, and whatever is coming, that is fine. But his actual nature can only be predicted once it comes under through some bad circumstances or some abnormal conditions like this. Now coming to the system. In a system, see, you just see the impulse response. Impulse response, such a bad input it is. At t equal to 0 it is infinity, and after t when not equal to 0 it is 0. You just assume such kind of input, which at t equal to 0 it is just like an impulse. It is just like a sudden push given to someone and he shows its real nature. It happens with the impulse response. Now impulse response, whenever it is applied to the system gives whatever is there inside that. Okay, practically it is like this, but mathematically using convolution we can prove that. Okay, whatever is there inside the system, ht, that will come out if the input is x of if the input is delta of t. So that's how the impulse response is, and that's how the impulse response relate to the life also. So when just assume that any input, is it possible to give such input first, and if it is generated such input at t equal to 0, which is infinity, and when t is not equal to 0 it is not there. That means it is just like a sudden push given to anyone, and see how the outcome comes. That is an impulse response. Okay, so such type of input is given to the system, which is a totally abnormal kind of input, and when this is given, the system behaves in such a way that whatever is there inside the system, that comes outside. Okay, that's how the impulse response is important. That's how the impulse response is defined, and that is very unique feature of the linear time invariant system. In system is not LTI system, impulse response and other things, there is no use to talk about that. Sahitya from Vizag is asking, xn equal to 1 at n equal to 0 and xn equal to 0 when n not equal to 0 for impulse function. If it is given that xn equal to k at n equal to 0, what does it? It is same as delta n. Yes, Sahit, it becomes, if xn equal to 1 n equal to 0 and 0 when n not equal to 0, it is nothing but equal to delta of n, right? If I write xn equals to k when n equal to 0 and 0 when n not equal to 0, it is nothing but k times of delta n. Finish. That is the only difference. But yes, it is also represents a delta function scaled by k. Okay, amplitude is scaled by k. This all the questions which we have. We'll continue with our class tomorrow again, and we have to study the Laplace transform tomorrow probably, and we'll do some problems of the impulse response. Okay, the impulse response, again, just see, this impulse response is very easy to understand. If you just give something to the system which is totally abnormal, just you want to give something, and then whatever is there inside, that comes outside, that is nothing but the impulse response. And such type of input which is only exists at t equal to 0, and that to existence at t equal to 0 is with infinite amount. After that it is not there. That gives the output. That gives the system behavior, that actual system how it is, that comes outside, and that is the impulse response of the system. Okay, let's do some problems which let's do some problems on convolution, which I was doing earlier. Delta of t minus t1, input is delta of t minus t0. What is going to be the output? Okay, in this case again, whatever we have taken, it becomes delta of t minus t naught minus t1. Finish. For example, if you have the input is delta of t plus 3, delta of t minus 3, you are going to get delta of t minus 3 plus 3, which is equals to delta of t. That is there. Okay. Very easy. Okay. Nothing is there. What happens? When ut is the input and delta t is the system response, you will get this as u of t. What happens to the system response? Yt. Now yt in this case is very easy. And this is u of t. Your ht is u of t like this. Input is also like this. Okay. Now what you can do is just do the convolution of this. You will have h of tau. This is t0. This input is time reversed, and then it is inserted into the system. Once it is inserted into the system, this common region will keep on increasing. Finally, it will keep on increasing, becomes infinite. So I can write here output yt is nothing but integral 0 to t 1.1 d tau, which is equals to t for t greater than equal to 0. That becomes a ramp function. So once you do the convolution of ut with ut, you are going to get a ramp function. Okay. Let us do the convolution of this. Okay. Now there are two pulses, both are of the same size and same pulse width. Now once I do the convolution of these two pulses, apply the same sum of the lower limits is 0 plus 0, sum of the upper limits is 3 plus 3, which is equal to 6. b1 plus a1 is 3 and b2 plus a1 is also 3, so that becomes 3. Instead of trapezium, this becomes a triangular, and at 3 I will get the value as 3. This is the net outcome when you convolve these two pulses. Subodh from Chandigarh is asking one doubt: if the performance of the system is converges, then the system is stable, and a divergent system is unstable. It's very correct, Subodh. This is the rule to identify whether the given system is converging or diverging. If the output of the system, it is diverging with increasing value of time, it is an unstable system, because at some value of time it becomes infinite. If the system output is converging, or even if it is constant, system is a stable system. Okay. Monica from Delhi is asking, the reason I told the two statements are contradictory because while calculating we did, scaling first and then shifting by t but in xt, but in checking time invariance we shifted the signal by putting in See, Monica, they both are two different things, where at one place I am doing the shifting operation on the given signal, and at the other place I have something which is already there, and on that I am doing the operation. Because see, in this place I am going reverse way. I want to know what is happening once I shifted the signal and want to see what is the output, right? So the output of the signal, if the input of the signal is x of t, then my output is yt equal to x of 2t. See this. For a given system is like this. Input is x of t, some system s1, and output becomes yt equal to x of 2t. I hope I have understood your problem. The reason I told the two statements are contradictory because while calculating s of v did scaling first. No, actually, see, we did scaling first, and then we did shifting is right. Whatever you are saying, that is, we have to shift it by t plus 2 by 3 in xt. But in checking the time invariance, if you want, we have time invariance property. The first thing is you have to shift the input. Okay, not you have to scale it. So first thing you have to shift it, and then you have to scale it. So once you shift this x by t minus t naught, output yt will be x of 2 of t minus t naught. But if you shift yt, this is what I want to say, because in checking the time invariance, the first tendency, see, what you have done is you have first scale it, right? Because it was given to you, you can either do scaling, you can either do shifting. But in the case of time invariance, the first thing what we have to do is we have to shift the signal, and then we have to do some operations. In this, the operation is the scaling operation, but the shifting has to be done first. Okay, that's why we are doing like this. It is not contradictory. It is only the requirement which we have to fulfill. For checking the time invariance thing, we have to shift it, and then we have to operate, then we have to do some operation on that and see what is the output, and then we have to shift the output and see what is there going to happen. If both the outputs are same, system is time invariant, otherwise not. Okay, I conclude my session here today, and we'll meet tomorrow, and we'll see the Laplace transforms and other things. We'll try to see gate problems. Probably by the time we have completed today, we must have some problems which we can solve it. Okay, thank you.